Hi everybody, welcome back. This is Unit 9, Lesson 7, and it is our final video of this unit. And what we're going to talk about in this little section here is what happens to certain properties of solvents, like water, when you add stuff to them. So when you add salt to water and when you add sugar to water, some of their properties change. And the properties that change are called colligative properties. And the more stuff you add to water, the greater the effect. So let's get down how they change, and then we'll talk about how the solute determines the effect of the change. So in your notes, we're in the final section here. Oop, there we go. Where did it go? It doesn't want to stay on that page. You have these little three things. When you add stuff to water, it changes the freezing point. Like, that's the whole reason we put salt on the roads in the wintertime or in spring, as you saw this past weekend, is because what salt does is it causes the snow and ice to melt, but then it also prevents it from refreezing, even though it's at a temperature below freezing. So when you add salt to water, instead of water freezing at 32 degrees Fahrenheit, which it normally freezes at, it actually freezes at a lower temperature. So solutes lower the freezing point of solvents. So it'll have to get colder for that water to refreeze. So it keeps water as a liquid even though it's below freezing. So solutes lower the freezing point of solvents. And again, the more you have, the greater the effect. Boiling point is opposite. Solutes raise the boiling point. Again, the more salt you add, the more solute you add to water, the greater the effect will be. Okay? And vapor pressure is lower. Solutes lower the vapor pressure. I like to think about vapor pressure and boiling point are related, so we'll talk about them real quick, and then we'll talk about how this is different. The effect is different for covalent and ionic things. This first picture here denotes what water would look like all by itself. So water will evaporate, and you'll create all kinds of water molecules. This is your vapor pressure on the solution. When you add salt to water, these little pluses here represent the salt. They're going to be attracted to the water. So think of them like anchors to the water. Okay? So these little red pluses will hold on to the water molecules in solution and prevent them from evaporating. So if you prevent the water from evaporating, there's not as much gas, there's a lower vapor pressure. And if you remember from our gases unit, boiling occurs when the VP equals the AP. So if there's less VP, you'll need to add more heat in order to make it boil. So you'll raise the boiling point. So when you add salt to water, for example, to cook pasta, it actually makes water boil at a higher temperature, okay? So your pasta might cook faster because it's hotter, but it'll take longer to get to that boiling point. Now, as we said, and I think it's worth, you need to write this down, the more solute dissolved, the greater the effect. And And that explains the difference between ionic solutes and covalent solutes. So if you take a look, I have a little animation to show you the difference between how covalent things dissolve compared to how ionic things dissolve right here.
Click on one of the buttons below to view an animation of that substance dissolving in water.
Okay, so NaCl is your ionic. Remember, that is a metal to a nonmetal. So watch what happens when you dissolve an ionic compound in water.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale.
It's like putting on Miss Frizzle glasses.
Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
And so when NaCl dissolves, you actually get two separate particles. You get Na plus and you get Cl minus. Okay? If we go back and look at the alcohol, this is methanol here. This is all nonmetals and there is no polyatomic, so this has covalent bonds.
Let's add a small amount of methanol, CH3OH, to water. Methanol dissolves in water. Click on the zoom in button to view methanol dissolving in water on a microscopic scale. Methanol molecules contain a polar OH group. The oxygen has a partial negative charge and the hydrogen has a partial positive charge. This charge separation is called a dipole. Methanol molecules are attracted to each other through the interaction of the dipole of one molecule with the dipole of another molecule. Water is also polar, and the dipole of water will interact with the dipole of methanol. The attractions between water molecules and a methanol molecule will break the attractions between methanol molecules, causing methanol to dissolve in water. Note that upon dissolving, the covalent methanol molecules remain intact. Compare this to the dissolution of an ionic compound such as sodium chloride, NaCl, which breaks apart into its component ions in water.
So, the bottom line is, whoops, sorry about that. The bottom line is that when you dissolve something ionic, whoopsie, where is it? When you dissolve something ionic, and we need to write this down, like any plus and minus, right? A metal to a nonmetal. That separates into more than one particle. So if you dissolve NaCl, you get two particles. If you dissolve CaCl2, you get three particles. Right? One calcium and two chlorines, or two chloride molecules. And as we said on the previous screen, the more solute you dissolve, the greater the effect. So if I added the same amount of sodium chloride and calcium chloride to ice, calcium chloride would do a better job at lowering the freezing point because it breaks down into more particles. Covalent things like that methanol that you just saw don't break apart. Okay, covalent things are all nonmetals. No polyatomics. So like this methanol, the CH3OH, which is right here. When that dissolves, you only get one particle. You don't break apart into ions because you're not made of ions. Only ionic compounds are made of ions. So the bottom line is that ionic things, and I want you to write this in your notes, ionic solutes lower the freezing point and raise the boiling point more than covalent. Because they love questions like the ones that you see in your notes there. And I'll give you a few more of these tomorrow as a warm-up while we're booting up our laptops to do the CASA learning. Okay? So if you look at this question, a 0.1 molal aqueous solution of which compound has the lowest freezing point? You want to pick the one that is ionic, the one that has a plus and a minus. And choice 1 is all nonmetals, so it's covalent. Choice 2 is all nonmetals, so it's covalent. Choice 3 is all nonmetals. Whoops, that looks like MMs. So it's covalent. Choice 4 is your metal. That's positive, bonded to your negative, polyatomic. That's ionic. And so this will break into one particle, this will break down into one particle, this will break down into one particle. But this guy will break down into 2 particles. It'll break down into Na plus and OH minus. And the more particles you break apart into, the lower the freezing point will be. So the right answer should be choice 4. That's it for tonight, everybody. We'll see you in class tomorrow where we wrap this unit up and test on Wednesday. Have a great night. Bye-bye.